links, concordance invariants, and Turaev genus. Let's welcome.
Thank you very much. Somehow, I'm not in my office. It's something like something called like conference room, and this is not my computer, and I don't know what's wrong with this microphone. So I'm using my phone to speak. Can you hear? Like, is it okay to? Is it okay?
Yeah.
Okay, good. So today I want to talk about. Before that, thank you for inviting me to the seminar to talk about my research. And so today I want to talk about something called concordance invariants and also a tribe genus. This is a joint work with Hongtaek Jung and Sunkyung Kang in the same Center for Geometry and Physics in Korea. So before we're going to talk about the tribe genus and the concordance invariant, I need to first talk about the alternating links. So I'm assuming that everyone is kind of familiar with the link, which is just a bunch of embedding of mutually disjoint embedding of S1 into S3, and whenever we have a link, it has many kind of properties, diagrammatic or topological. We are mainly interested in something like more diagrammatic thing. So, which is one of the famous things is something called alternating. A link is alternating if it admits an alternating diagram. So, for example, this is the one of the famous non-trivial knot, which is a trefoil. It was a long-standing question by Ralph Fox, which was asking what is an alternating knot? Because as I told, its original definition was needed some projection onto a plane or S2 so that it satisfies the combinatorial description. But it somehow this combinatorial property has a lot of geometric and topological interesting properties. So like this is natural question that like then what is this alternating in a topological sense? And in 2015, Josh Green and Josh Hawley almost simultaneously and independently gave this topological characterization of alternating links using a pair of spanning surfaces. So it is somehow like after that we have a lot of things, a lot of works are done after this work, and one of them was like trying to generalize this characterization to some generalized alternating link.
So have you looked at my books where I wrote a lot about atom genus, and atom genus is actually the same as Turaev genus, but we also had surfaces, and it was done long ago. Well, just not theory books, not many others.
I didn't know atom genus. Is it the same as the Turaev genus?
It is the same as Turaev genus, but possibly you should have looked at my book. So there were many books and papers on atom genus and Turaev genus on the archive and so on.
Oh, I see. I think maybe at some point I looked at it, but mainly this Turaev genus one was like when I was in like graduate school. I mean, this is the most recent result like last year, but maybe I don't remember right now. But I will look at it. Thank you for
No. For me, it's important what Green and Howie did because, well, possibly this was already known. So you said it was. Well, I'm pretty sure that many things was done by Turaev himself and maybe by myself.
Oh, so the characterization of Howie is actually if a knot admits some pair of spanning surfaces which satisfies certain equation, which combining the slope of the spanning surface with its Euler characteristic, then so this existence of pair of spanning surfaces implies the knot is just an alternate.
Okay, it's interesting.
Yeah. So And Green's is more delicate. He defined something called a positive definite and negative definite surface. And his characterizations, actually, I don't remember exactly, but it was like Z-mod 2 homology spheres. So a knot admits something like a pair of positive and negative definite surface in Z2 homology sphere. Then it is actually a knot, like a knot or link in alternating link in an S3. So this Z2 homology sphere becomes S3. So Green's characterization is slightly more general, and Ho is more geometric. I mean, I like a more kind of elementary characterization. But there's a weak gap in the archive. So anyway, so this like they're defined this alternating knots and links in terms of the pair of spanning surfaces with the certain satisfying certain properties. So that's a characterization. So okay. So then we're interested in some trying to think about the generalization of alternating link, and there's a bunch of generalizations of alternating links. The first is the very easy generalization, which is almost alternating link, which is if it admits some diagram which changed after some crossing changes, like one crossing change. And more generally, this K almost alternating link is like it admits a diagram which can change it by K crossing changes. So this can be defined. And second one is toroidally alternating links, originally defined by Colin Adams, which has not a link has a very nice alternating diagram on Higgs-Torus in S3. It can be generalized to something called a surface alternating link, defined by Hayashi, which is like it has an alternating diagram on the higher genus Higgs surface of S3. And third one is a Turaev surface, and it's actually related to the second one, but it has some. We need to think about the construction, so I'm going to describe it later. And the last one is something called quasi-alternating links. I think it is originally defined by Osbach and Szabo in terms of the Higgs flow theory. So today I'm going to talk about Turaev surface and the quasi-alternating link. So I'm going to first talk about what is Turaev surface. So this was actually, historically, this was introduced by Turaev to give a different proof of the Tate conjecture. I'm pretty sure that this is much simpler than original proof. So the Tate conjecture is just an alternating diagram realizes minimal crossing over. So if we have some diagram of a knot, then for each crossing, we can define a smoothing. People use the different words, but I prefer to saying smoothings. So as in the notion of Kaufman's bracket polynomial. So for each crossing, we can do smoothing in an A way, which is on the left, and the smoothing B smoothings, as in the on the right, the green color. Then what we can do is for each crossing we smooth. For each crossing we can do the smoothing, and what we're going to do is for every crossing we are doing the A smoothing for every crossing. Then we get some circles on some mutually disjoint circles on the plane, and we are going to push these circles above, and we smooth every crossing in the B smoothing. We do the B smoothing for every crossing, and we pushing it down, and we're trying to building a cobordism from top to the bottom, which is locally modeled in like this. So in the saddle point, you actually can see a crossing of an original diagram. Then we can build some cobordism from the all A smoothing circle, all A smoothing circles obtained from the all A smoothings, which I will call the all A state. and to the OB state, which is obtained from the B smoothing every crossing. And then we cap off the each of the boundary with just a trivial cap off the disk. Then we obtain some closed surface, and we are going to call it a Turaev surface. Actually, I think the original paper of Turaev didn't cap off, but we are going to think about the closed surface. So I'm going to cap off every boundary component and I think about the closed surface. So this is an example. So we're starting from the leftmost figure, and in the middle, the top one is all A state obtained by A smoothing all crossings, and the bottom one is all B state, which obtained from B smoothing all crossings. And then we're reading a cobordism, like in the rightmost figure, and then we are going to cap off the boundary to the disk, and we got some closed surface, which I would call the Turaev surface. So this is I think this probably helps you to understand what kind of surface that I'm talking about. So this Turaev surface has a very nice properties. The first one is actually, it turns out that this is just a Higgs surface of S3. So somehow, if you're not familiar with the Higgs surface, then you can think that this is kind of unknotted in S3. And second, from the construction, link has some induced link diagram on its Turaev surface. And it turns out that using the orientation of the surface, we can say which part is overcrossing and which part is undercrossing. Then we can figure out that this induced link diagram is actually alternating on the Turaev surface. And third, from the construction also, this induced link diagram cuts the Turaev surface into disks, which I will call cellularly embedded. So this is an example of Turaev surface of the Preslin link and the diagram. So the board color, the board line part is actually in the toward to us, and that is light colored arcs are is actually backward on the screen. So you can see that if you can check that, even it looks like this is non-alternating. But if you think that this diagram lives on the torus and you're thinking about the torus, the up and down in the torus, then you can see that this over and under information changes whenever you turning around the torus, so that it becomes an alternating diagram of the torus. And also you can check that if you think of this diagram as a four valence graph from the torus, then this four valence graph cuts the surface into several disks. Have any questions?
There were some with estimates for Khovanov homology and also for Higgs-Floer homology coming from the surface.
Oh yeah, I'm going to talk about that later. Yeah. This is just right now. It's just a definition.
Okay.
Good. And the first one is actually a link is alternating if and only if there exists a diagram such that its Turaev surface is sphere. So somehow this is like you can think that this is somehow can generalize the alternating knot, because somehow everything can be alternating on some Higgs surface. So everything can be somehow considered to be some alternating links on some surface. So this is kind of interesting notions and an observation. But by the way, the question is not every, so we can so from these properties we can actually naturally think about this question, which is suppose if I give you some Higgs surface and we are drawing some alternating diagram of the Higgs surface in such a way that they cuts the surface into this, then is it always comes from the Turaev surface construction? And the answer is actually no, because it turns out that to become a Turaev surface, you always can find some essential curve on the Higgs surface which transversely intersect the knot diagram in only 2 points. I mean, like we're not going to intersecting on the vertex, but like intersecting as transversely. Like we need to find, we always need to can find such a circle which intersect the diagram twice on the Turaev surface. But this diagram, alternating, cellularly embedded, but there's no essential curve on the torus intersect this diagram in 2 points. So this does not come from the Turaev surface construction. And moreover, this one I'm going to talk about later. And also, it turns out that Armand, Turaev, and Kindred give an if and only condition for a given cellularly embedded alternating diagram on a Higgs surface is an alternating diagram on the Turaev surface. So some combinatorial condition should be satisfied to be actually comes from Turaev surface construction. So we just talked about the Turaev surface. Now I'm going to talk about some geometry invariant of norm, which is called a Turaev genus. So its Turaev genus, its definition is it's like a crossing number or like a separate genus. The Turaev genus with link is just the smallest genus among all possible Turaev surfaces of length L. And there's a lot of things known about it. The Turaev genus of a link is 0 if and only if a link is alternating. And the width of Kwan homology and not flow homology gives lower bounds. This was, I think, independently done by many authors. And also an etiquette diagram, so etiquette knot, the Turaev genus is known for every etiquette knot because it comes from the etiquette diagram. It's just the minimal Turaev genus realizes from the etiquette diagram. This was done by Tetsuya Abe.
Just a moment. So adequate knot, I'm interested in the following question. Do we have any non-adequate diagrams which realize the Turaev genus? So this number three, number three, yes, I think yes. I think number 3 was proved in my book also. But what about non-adequate knots which realize the Turaev genus? Because you see, there are two estimates. So the span of the Kaufman bracket is 4n minus 4g, and the thickness of the Turaev genus is less than 2 plus g. So if we know that for some link we have both equalities, then this link is minimal. So for adequate diagrams, we know that they are minimal by themselves. But I'm interested in other non-adequate diagrams when we have it.
So you can actually, so the simplest answer is just taking some petzels, which is known to be non-alternating, but which is not adequate also. Then the pretzel diagram realized the Turaev genus 1, and it is not alternating, so it is at least 1, so it is just 1.
Yes, so I'm asking you, yes, but there the Turaev genus is just 1. Okay, so please let us write it by email. So then we have a huge amount of diagrams which are non-adequate and non-alternating and which are minimal. So this will be an application. This will be an application for you know, this will be an application of these two things, Kaufman plus Khovanov to minimality, to crossing number.
Yeah.
Okay, so please send these things to us by email.
What email? What?
Yes, I mean these examples, how to refer to these examples. Well, of course, it's not good to talk by words. It's better to discuss them by emails. So then we get.
So later on, I'm gonna put some examples which we didn't know the exact striped genus previously, but now it is known. I think they are definitely not adequate because it was, because if it was adequate, then we know the striped genus, and I'm going to present some examples soon. So
yes. Okay, so send them by email also.
So and also a signature and Osbach tau invariant. And S invariant can give the lower bound, which is like combining, just combining any of the two of them, and combining in such a way that tau plus sigma over 2, S plus sigma over 2, tau minus S over 2, and they are all lower bounds of different stripes. So I think this was done by Dasbach and Lawrence. And then one of my PhD work was actually try to characterize tribe genus 1 knots, but we are not kind of able to do, but we characterize the tribe genus 1 diagram. So
just before we continue, really embarrassing question. So I'm a non-expert. What does adequate actually mean for knots?
What is the best way to say adequate? So consider so if you have a knot and you're doing the cross smoothings, you can do the smoothings and A smoothing and B smoothing. And suppose that you're think about the all A state coming from A smoothing, every crossing crossing changes, and what is it, smoothing a smoothing for every crossing, and then all B state, then actually what you can do is whenever you're smoothing, you connect, you're actually kind of adding an arc there to keep track of the crossing. Then you actually get some graphs, which you can think that the circles becomes a vertex and the edges becomes the edge of the graph. And whenever adequate means all the graph comes from all A state and the graph comes from all B state, both doesn't have a loop.
So they're just trees? Is that what you mean?
No, just it doesn't have just a single loop. It can have a circuit.
Okay.
Have a loop.
I see. Okay.
Yeah.
I see what you mean. Okay.
Also, in other words, like you can define it using the tribe surface, but I just don't recommend.
Okay, but somehow you only need to check this condition for the two extremal cases with the all A crossings and all B crossings. Resolutions. Okay, I see. Okay, thanks.
One more question. So, is there any analog of the Tate-Flipping conjecture if we use not derived genus 0 but derived genus 1?
So I think is a kind of yes or no, because I don't remember exactly, but like a long time ago I see the paper, something says they're not talking about the links in S3 and taking in S3, but instead they're taking a link in a thickened surface, and there have some kind of flipping theorem in a thickened surface.
Well, you see, for flipping theorem and thickened surface, it's something like virtual knots. I spent many years in virtual knots, but I'm interested just in the sphere. So assume we have something which has genus not 0, but maybe genus 1. So do we have any chance? Well, it's a step towards classification of links which are not alternating. It would be very great.
Actually,
yeah.
So actually, that was like when I was a graduate student, my advisor Ilya Kofman like asked me to pursue that problem, like proving like Gleichen conjecture for tribe genus 1, something like that. But I never succeeded.
Okay, so let's discuss it also afterwards.
Yeah. Oh, okay. Nice. So the diagram characterization is basically, so if you're not linked amidst this kind of diagram, so it is, so you can see that this green discs and some black arcs connecting them. So actually, I will describe a little bit. This green disc is they are actually alternating tangles, and this black arcs connecting them is actually non-alternating edge of a diagram, not diagram. So if your not diagram looks like this, then it's tribe genus 1, and the tribe genus 1 diagram always should looks like this. So this is a kind of diagrammatic characterization.
Well, so I don't see where it is non-alternating. So we have no crossings in between.
So between two. So can you see my mouse?
Yes.
I might using. I think it has some options. Can you? Oh no. There's. So this is an alternating tangle, and this is alternating tangle, but they are connecting in a non-alternating way.
Oh, okay.
Yeah. So these are like all these black arcs actually like connecting alternating tangles in non-alternating. That's basically what I was saying. This notion was introduced by Wesselthwaite, and I think he says something like alternating tangle structure. So I think you can Google and finding Wesselthwaite alternating tangle, then you can easily find like how you can obtain such a link, such a tangle structure from the diagram. But it's very simple. Yeah. Anyway, so this we call alternating tangle structure. Basically, we are dividing every pieces into the alternating tangles, and if not diagram admits such a alternating tangle structure, then its diagram is tribe genus. And also, in fact, the tribe genus of a diagram is just determined by an alternating tangle structure. It doesn't depend on what's inside in this green disk. The genus of a tribe genus of a diagram, not a knot, but the diagram is just defined by this tangle structure. And after this work, Kofman and Lawrence find the signature and the Jones polynomial and the Kovanov homology condition for the tribe genus 1 knots. I forgot the Kovanov homology condition and the signature, but the most interesting fact was actually the Jones polynomial part, which is the tribe genus 1 knot should be monic. So this maximal degree or minimal degree, like the coefficient of the maximal degree or minimal degree term should be, at least one of them should be plus minus 1. And then this is also not very familiar to me, but somehow like it's a quite recent. I think it was the last year. Capro, Gonzalez, Lee, Lawrence, Sosnovic, Zhang proved that lower bounds also can be obtained from Lee and Barnard spectral sequences. But I'm not good at spectral sequences, so this is the only thing that I can tell. But this is somehow like the most recent result about the lower bounds that I'm aware of. Except our work. And before talking about our result, I just want to say talk about some problems. The first thing is it is not known that almost alternate. So this almost alternating knots is automatically the almost alternating diagram is just the tribe genus 1. So if it is not alternating but almost alternating, then it's tribe genus 1. But I think it was the conjecture from the Abe that is the tribe genus 1 knots are always almost alternating, but this is still open. And myself proved that is actually true for inadequate tribe genus 1 link. Inadequate means it's totally like a opposite, like it is totally opposite from adequate, which is this the graph from all A state and all B state both should have like every diagram taking a A state graph and B state graph, then they always admit the loop. That's the inadequate. And this is true for inadequate tribe genus 1 link, but we don't know that it is true for semi-adequate. So semi-adequate means like at least one of them doesn't have a loop. And just related to that, I myself also my PhD work was I characterized toroidally alternating knots and also almost alternating knots topologically in terms like in the sense of like it's just always characterization of alternating knots. So maybe, but they are really look similar. So my hope is probably they're like almost, I mean, they're same, but I also could improve. And the problem of my characterization is the condition is a little bit technical. So I don't know how to apply this to solve this problem. Anyway, this is an open problem. And second, this is a funny question. Is there any inadequate tribe genus 1 link? We don't know. So maybe my theorem is for just for empty set. I try to find inadequate tribe genus 1 link for a long time, but the only thing that I can tell is like that usually whenever people want to say something is inadequate, they're looking at the Jones polynomial and they're looking at the coefficient, the maximal and minimal degree coefficient. But because of the work of this Dasbach and Lawrence, the Jones polynomial should be monic. So the only thing that we can say is probably they're like everything's just undeterminate. Like it's just it's vague. We don't know. So this is I don't know how to attack. Just totally I don't know how to attack. So I mentioned this. And third is Jones conjecture, the Jones unknotting conjecture. You know, the Jones polynomial detects the unknot is true for tribe genus 2 knots because it's true for alternating adequate knots and also the tribe genus 1 knots. And the last one was done by Adam Lawrence, and I think he's one of his students. And the first one is kind of it's just my question, which is the tribe genus is always strictly less than the separate genus for positive knots. So usually tribe genus and the separate genus doesn't have any relationship. But interestingly, positive knots, they have the tribe genus is always less than equal to the separate genus. And this conjecture is true for positive knots with separate genus 1 and 2. So my question is it true for any positive knots? And I also don't have any. I thought that I have a proof, but I think a long time ago, it was like 5 years ago, and I found a mistake there, but I never tried after that. But and the fifth one is what is the topological characterization of the tribe surface? The reason why I'm talking about this problem is if we can characterize the tribe surface, then what we can do is actually we can characterize many different diagrammatic properties such as the positivity or adequacy like that. So, and also just the one notice, the Carpagiani using the tribe surface crossing number and the color Jones polynomial to characterize the adequate knots. So, but the problem is we don't know the crossing number. We don't know what is tribe surface in a topological way. So it is kind of still like we have a bunch of things to work on. So this is a open problem for that. And so track surface is done. Not done, but like kind of I introduced enough. And I'm going to move on to the quasi-alternating links. So the quasi-alternating links defined in the following way. This is defined recursively. The set of quasi-alternating links is the small set of links that is defined the following properties. So the first unknown is like this quasi-alternate set of quasi-alternate link, and if the link is has a and if the link has a diagram L such that it has some crossing C, in that diagram there is some crossing C, so that if you both smoothings are quasi-alternating and also they are satisfying this determinant equation, then this link calling L is also a quasi-alternating. So this is somehow like recursively defined, and it is whether like we don't know much about the quasi-alternating because the definition itself is really complicated. But people studied a lot because it has some nice thing with the Higger floor, and this is motivated from the Higger floor.
So is it the product of determinants or sum determinants?
Some.
Okay.
So first of all, the Osbos and Stauber show that alternating links are always quasi-alternating, and twofold branch to cover a quasi-alternate link is in the L space, which means it has just the simplest Higger floor homology, and it's a homologically thin, which means the width of the common opening Higger floor homology they are just a 0. And its homologically thin property says this S invariant is just the same as the negative of the signature, and tau is also determined by the signature. And it is known that connected sums of quasi-alternating knots are quasi-alternating. And like, as I told, this quasi-alternating links defined in a very complicated way. So, so the issue is whether how can we generate this quasi-alternating link? It's like not which is non-alternating, but Champanerkar-Kofman somehow if we know that something is quasi-alternating, then we are taking that quasi-alternating diagram and exchange that quasi-alternating crossing to some rational tangle, alternating rational tangle, then the knot is still quasi-alternating. We show that. So this is somehow we can generate the kind of like infinite family of the quasi-alternating knot. But the problem is, this was open. We show that this is actually true, but I mean the question before the open conjecture was do there exist a quasi-alternate with the arbitrary Turaev genus? The reason why this question was meaningful is actually all this lower bounds of the Turaev genus vanishing for the quasi-alternating. They just give a trivial bound, like everything just is okay. It is greater than or equal to 0. And also the problem is this twisting method from Champanerkar-Kofman. The diagram does not change. The Turaev genus of a diagram does not change it by this operation. So we don't have any hope that like we can probably produce some examples of some quasi-alternating knots with the arbitrary Turaev genus. Also, the third, I forgot to write it here. The problem is we don't know that Turaev genus is additive under connected sum. The separate genus is additive under connected sum, but the Turaev genus we don't know. So we also can't do the connected sums. Just so like nothing works before our work. So this was a so this was a question we are trying to answer, and we succeed to answer. To go into our detailed work is just talking about some previous work before our work. We know that quasi-alternating pretzel links and Montesinus links, we know it, and their Turaev genus is 1. And using this, the monic Jones polynomial stuff, Adam Lawrence tells us that these knots were known to be quasi-alternating and Turaev genus too. So the one of the example I drew in here, so N873, this was Turaev genus 2, which was known from the diagrammatic computation plus this Jones polynomial obstruction of the Turaev genus 1 knots. And yeah, this was known. But higher genus, no, we don't have anything before. So so to describe our original work, I first need to define something called DL invariant. Before that, I want to make some notation, like some symbols. I want to describe some symbols. This S A of D, or respectively S B of D, is just the number of all A state circles of D, or like respectively number of all B state circles of D. And M plus D, respectively M minus D, their number of positive or negative crossings of a diagram D. And oriented band surgery of a link is a local modification of a link, as in the figure below, which is this. So we are adding a band in a coherent way. I just say this is oriented band surgery. Sometimes it's called coherent band surgery, whatever terms you're familiar, you can use. Then now we can define the DL invariant. This is just an oriented link invariant, which is invariant under overall orientation reversal, satisfying the following conditions. The first is actually if you can build some oriented cobordism, I mean, basically you're obtain a link L from a knot K using some oriented band surgeries, then this the difference between those two values are bounded by the number of the oriented band surgeries that we performed. And second thing is,
so there is a question whether nu is integer. I think so. No.
The one is the number one. This invariant, we don't know that it doesn't need to be integer valid invariant. It could be some real number, I think.
Well, I don't understand. So is it one invariant or is it a family of invariant?
It turns out that this is a family of invariant. But I mean, a link, we call this invariant is just a DL whenever it satisfies these conditions. So it's a family of invariant. And second thing is, for any positive or negative respective negative diagram D of non-split positive and negative link L, they're satisfying some technical condition. I'm going to describe why I'm putting this technical condition later on, but so this is what we call you're calling us the DL, the set of DL invariant. So okay, sorry, I think I didn't bring the parts where it describes why this is meaningful. So what you can do is actually, if you take the difference between, like suppose that you have choosing some two different DL invariants and taking a difference, then what you can see is you need to subtract one from the other. Then what you can get is you actually get the Turaev genus, somehow like Turaev genus from this equation. That's why we put this inequality. And this was motivated by the work of Adam Lawrence and Oliver Dasmash, because they show that signature and S and tau invariants all satisfying these inequalities. And we think that maybe this is just some kind of universal properties. So we are just copying their properties and put it as our condition here. Have any questions? So first, the example of the area invariant, like what I just said, the Rasmussen S invariant, and some this generalization of SN invariant, this SLN coming from SLN homology with a suitable normalization. So we have an infinite family here, and negativity is not signature. And the modification of any slice torus link invariant in this way, they become like all DL invariant. For example, this Oswald tau invariant is just a 2 tau minus L. L is the number of component, plus 1 is just the DL invariant. So yeah, so this is like a kind of we are putting the like what kind of condition that we need, like we're just pulling out and making a set of invariant, and we know that from the previous works, these are just set like just infinite family of the link invariant. And our main theorem, motivated from the dot function Lorentz work, is the difference, the half of the difference between any two DL invariants is the lower bound of the Turaev genus. So you can use, like, if something doesn't work, you can use whatever, like choose some DL invariant and like just taking the difference, then you probably can get it. Hopefully you can get this some very nice.
By the way, do you have any estimates for the four-ball genus and slice genus coming from the Turaev surface?
I don't think so. The only thing that I know is like what I said. For the positive nonce, Turaev genus is smaller than equal to the separate genus, and then we know the positive nonce. The separate genus is same as the slice genus. That's the only thing that I know. And this is the difference between two concordance invariants. So I'm not sure. Maybe if one is vanishing, we know that if something is vanishing and something is not vanishing, then maybe their Turaev genus can relate it to the slice genus, but we don't know in general.
You see, recently the problem about sliceness, actually non-sliceness, about non-sliceness was proved by Lisa Piccirillo, and she said, well, Rasmussen is not sufficient here. Well, I hope that there will be some way of doing many things for estimating slice genera or something else, not by using Rasmussen invariants, but by using something without knot homology. And I think we should look at more carefully of just at those surfaces and what we can do in higher dimensional spaces.
Well, they're very nice, but I didn't thought about it. But they're very nice. I actually trying to somehow like showing some like all the results, like all the complicated results using the kind of alternating properties of the alternating thing, but didn't really successful. We can talk later about like what I did or like some kind of things. Yeah. Can I go? Can I?
Yeah, sure.
Proceed. Yeah, sure. So the corollary of this one is actually for each integer g here, infinitely many quasi-alternating nonce for Turaev genus equals g. I feel, but isn't it? Oh.
So what are we proving?
So we're going to prove the following lemma. So in the proof of KBL not and DB is diagram, then we have just and this nu be a DL invariant, then we have just the same inequalities like in the DL invariant definition. So the difference is, you're like a little bit carefully, is this is for any knot and any diagram, but our DL invariant, it doesn't need to satisfy this inequality doesn't need to be satisfied for every knot or diagram, but just only for a positive or negative diagram of a positive or negative link. But actually, it turns out that if we only require that positive and negative thing, then we are enough to say that, like, this is enough to say that every diagram in a knot satisfying this inequality. How much time do we have left? Actually? 7 minutes?
No, 37 minutes.
Oh, nice. Okay. So, I put it here. So, suppose we are having two DL invariant. If we take a difference, then you can compute it, and it is just a Turaev genus of diagram, and that's why I put it here. Okay, that's nice. The difference is, using this inequality, we can see that difference between any two DL invariant is bounded above by the 2 times the Turaev genus, and that's why we are putting this kind of technical condition in the beginning, and the theorem is just like, I mean, if we show this lemma, then everything is just trivial. So note that the DL invariant only requires that the inequality holds for positive and negative classes. Okay, so let's talk about the proof. Sketch of the proof. So first, I just drew some examples to making sure that we are working on just to help to understand what's going on. So starting from some diagram, and what I'm going to do is first do the A smoothing for every positive crossing of a diagram, and actually this is same as the cipher smoothing for this crossing. Then what we are going to do is we are choosing so we can consider each of the component, this not components is a vertex, and these edges coming from the smoothings are edges. Then we have some graph, and we're going to take some tree, the spanning tree there. We're going to take some spanning tree, and what we are going to do is we are removing all this. We are taking some spanning tree, and then we are undo the A smoothing for the edges of this spanning tree. Then we are getting some knot diagram here. And what we are going to do is we are actually, so this is not a good way to draw, but I just, for simplicity, I drew it like that. But we are going to untwisting all this diagram to make another diagram. Because we choose the spanning tree, so we can from the leaf of the tree, we can flipping so that without changing any other crossing, we can just removing all this crossing from the edges of the spanning tree. So this can be done. Then what we get is actually, so just a notice, we first smooth every positive crossing, and we unsmooth certain positive crossing, but we are untwisting to removing it. So remaining diagram is just a negative diagram. So there's no positive crossing remaining. And I can't see my slide. Okay. And the number of the circles in OA state of this last diagram, the bar, is if you think a little bit carefully, then it's just the same as the number of the circles in one of the state of the original diagram D, obtained by A smoothing or crossings of D, except the crossings corresponding to the edges of the spanning tree T, and then smoothing B smoothing remaining positive crossings. So these are just the same. So from this observation, what we have is the number of the OA state circles is actually number of all A-state circles of the original diagram D minus the number of edges in the spanning tree that we choose. So this is a equality. Also, there's the knot represented by this diagram D bar is actually constructed from adding the number of positive crossings minus the number of edges oriented saddles on K. So what it means is like we are smoothing like this remaining crossings with the oriented saddles. So the difference, this DL invariant by definition, the difference between this do is actually M plus D minus ET, the number of edges of the spanning tree. Then this new K bar we can estimate, which is it's actually less than 1 plus the number of positive crossing of D bar minus the OA state number of OA state circles of D bar comes from the condition of the DL invariant, like definition of the DL invariant, and we plug in the number 2, the inequality SAD bar is SAD minus ET. We plug in, and also as I said, this D bar is a negative diagram, so M plus D bar is 0. So we have this new K bar is 1 minus SAD plus ET. Then we can mixing up 3 and 4. Then what you have is just a new K is just less than equal to 1 plus the number of positive crossing of D, and then number of all A state circles in number of all A state circles. So we prove the one part of the inequality, and the other side of the inequality is actually you just dualize everything. You're doing B smoothing, and then you do the same thing, then you get the same inequality. So we are proving the lemma. And because of this computation the middle computation, and then we see that the difference between any two DL invariant gives the lower bound of the Turaev genus. I mean, half of the difference gives the lower bound of the Turaev genus. And somehow my talk is finishing very quickly. I didn't expect. And the proof of the corollary is very, by the way, before going to, do you have any questions so far?
Some questions are written on the chat line. Maybe these are not just questions, but suggestions. It would be nice to invent Turaev genus for cobordisms, for 2 surfaces, for 2 knots. So there are many questions on the chat line. Okay.
So your question is, what is the Turaev surface for 2 knots? Like the surface in the 4 space?
Yes, I think so. Well, actually, I'm very interested in the question whether we can get an analog of the Kaufman bracket for 2-dimensional objects. Actually, it's really very important. So if we can, then this will be a pictorial analog of many things. So I want to have it. Well, in some sense, we have Lee Sang-yul and Kim Ji-yeon and Jung Ye-won, but this is not satisfactory because this is not a polynomial. It's a sort of, so for 2 knots, we have some specific values and we have to, so I would be happy to have some things like Kaufman bracket for 2 knots and also atom genus and similar things.
Yeah, so first of all, I also thought about like what is the Turaev genus for alternating Turaev surface for like what is a Turaev hypersurface for higher genus knots. But the problem is that we need to define the first what is an alternating there. You can define it for the ribbon 2 knots, but this is not kind of very interesting. and I was thinking about like somehow can we somehow. So I talked with Jeff Meyer a long time ago. We talked about can we somehow using this Josh Green and Howey's character, like we do the reverse engineering from the Josh Howey and Josh Green's this characterization of the alternating knot. But the problem was what was the problem? The problem was somehow we are not be able to. So because of they are bounding a three manifold, and you know whenever for a knot the surface is weird enough to say talking about this is first homology, but the three manifold it doesn't. And also somehow they're thinking that this pair of surfaces can intersecting in a very nicely, like you know whenever, so like just the diagonal definition, we taking a projection, and they're somehow we do the. So basically Josh Howey's characterization is basically here, if we admit, so coming from this reduced alternating diagram and taking a checkerboard surface, black and white surface, basically that pair of surface becomes the checkerboard surface of a diagram. But they could do it because they are intersecting very nicely. They are intersecting the proper arcs for each crossing, and you're squeezing your deformation retract, you get the sphere, projection sphere. They're very nice, but the problem is for the higher dimensional knot, this solid, cipher solid, they can intersecting in a crazy way. They are three intersecting in fours. Their intersection pattern is like surfaces, closed surfaces. And we are not like we thought about it for a long time, but like I mean, I'm happy to talk about how to generalize geometrically Turaev surface. That's also good. And the second thing, I also realized this. I also knew that this Sunkyung, Lee, and like people's this Kofman thing. And in one of the conference, I actually suggest the problem about like can we somehow define some polynomial invariant of the higher genus, higher dimensional knots, because like one of my work with my collaborators was actually we are actually find the complete set of moves of knotted surfaces in arbitrary closed orientable form manifold. So like my question was like, can we define some invariant in a general arbitrary form manifold? Like, can you define some nice invariant there? But I also don't know how to do it because we have too much moves, and I just don't have any ideas to do it. I mean, it's actually like more than like I think 2 or 3 or 4 more moves than this this, what is it? Nakanishi? No, this like you know that this one of the Japanese mathematician, and after like this Frank Swanton and then Curtin and Cullen, like there were like this moves, banded on linked moves. We are generalized to the arbitrary form manifold, but we need to introduce a lot of moves there. So yeah, I don't know how to do it. Anyway, but that's also interesting question. Can I proceed?
Sure.
Okay. So my last part. So I think we can finish. We finish very quickly. The corollary, the proof of the corollary is very simple. So we know that. So this pretzel knots, the p 2p plus 1 minus 2q minus 1 comma 2. This one is like we are actually like this usual pretzel diagram. Sorry, I forgot to put the figure. So 2p plus 1 and 2 and minus something. So this pretzel knots We know that this is a quasi-alternating. I think it was a work of maybe Josh Green or like Champanerkar-Kofman. I forgot who did this, but these crystals are quasi-alternating, and also they are non-alternating, and the Turaev genus is 1. And what we are going to do is we are basically, our strategy is to just connected summing. As I said, we don't know the Turaev genus is additive under connected sum, but we can show that this case, whenever we connected sum, like same copies again and again in the Turaev genus, just increasing like a linear. We know it. So the computation borrowed from this previous verse, which is the invariant, which is just the same as the signature because it's a quasi-alternating, and it is just 2p minus q. But this Sn invariant, normalized Sn invariant, is actually either 2 times p minus q minus 2 or 2 times p minus q minus 2 plus 2 over n minus 1. I think it was a computation by Lucas Lewald and probably Andrew Law. Then what we can do is just Sn invariants are just additive under connected sum. So we are we are adding to the connected sum. Then we do the computation. Then this Turaev genus is bounded below by this g minus g over n minus 1. Then if n is big enough, actually it doesn't need to be n is big enough, but no, it should be n is big enough. Sorry, if n is big enough, then the Turaev genus is less than equal to g, and we know that it cannot be greater than equal to g. So this should be exactly g. So
well, you see, I had some estimates for the atom genus coming from something like satellite nodes. So we can take cables and we can try to estimate some things. So these things are written in my book. So actually, this is the way we can prove that for adequate nodes. For adequate nodes, we can prove that they are well good by using by using cables. So cables are somehow similar to multiple. Yeah. Okay.
Oh, this is really nice. Didn't know. I need to look at the atom genus. I somehow I probably like missed the.
Just look at my books and papers. So well, it's something like 15 years ago.
Yeah.
Okay.
Thank you so much. So actually, this is the end of my talk. Somehow, yeah, it's a little bit. I didn't expect to finish this early, but yeah. So this is this is the end of my talk. So do you have any questions?
So thank you very much. It's an interesting talk. So very interesting things. So let's discuss many things afterwards by email. Are there any further questions or comments? Please unmute your microphone or write in the chat line, whatever way you want.
Oh, thank you for an interesting talk. I have a question on page 22.
22.
Yeah. Basic question. Yeah. Here you say the spanning tree T. Yeah. I'm not sure the spanning tree of what? Spanning what?
So from this knot diagram,
yeah.
I choose the positive crossings. I choose the positive crossings, and then I smoothing. Then I consider each of these knotting pieces as a vertex.
Okay. Okay.
Then we can see that this graph structure.
Yes. That this is a loop, right?
Yeah. I mean,
Oh.
Like, this, did I miss something? Oh, sorry. Yeah, this one's really, yeah.
Oh. Okay. So if I don't misunderstand,
Yeah.
I think you mean you first give a tangle, alternating tangle decomposition, then you choose the spanning tree of such a graph, right?
No, it's not an alternating tangle decomposition. It's each of the pieces are just these are just a negative diagram.
Negative
Yeah.
diagram.
Yeah, negative. But they're not connected as a diagram, but they're disconnected as a diagram. So, and all these pieces becomes a vertex.
Okay.
And you're taking a graph from here, and then you choose this spanning tree. Like there's no such thing here, and also there's no such thing. Sorry, there's no such thing, and then here. Yeah, this is a spanning tree. Sorry, I misdrew a little bit.
Okay. Any further questions or comments, remarks?
And I want to ask about the Howe and Green's result. Is it a recent result or
it's a 2015. It's a 2015. I think it's a kind of like October 2015 or something, November.
Okay.
So it's 6 years old. Almost 5 or 6 years old.
I heard you said that this result use two surfaces, use two spanning surfaces, right?
Yes.
Just the A state surface and the B state surface. Actually.
Yes.
Okay, but why it can be called topological characterization? Because for example, if you use Turaev surface, then you can still ask what is the topological characterization of Turaev surface. Yeah, why it can be called a totally topological characterization for alternating knots?
Because like it's just saying existence of the two spanning surface with just a certain condition, then the knot is alternating. That's why they call topological. Like they don't have a projection. They don't have a like it admits some diagram. They don't have a map. They just say if a knot complement in a knot complement there is this a two surface, two spanning surface, such that the slope difference and slopes and all the characteristic, the summation, it becomes 2 or something, then it is alternating. And also it is alternating, then you always can find such a pair of surface. So that's why they say topological characterization.
Okay, where can we see the papers?
I think it's also published. Like one of I think Josh Howard's paper was published in GT, and Josh Green's paper was published in Duke. So you can find there, or archive. Just archive Josh Green or Josh Howe, and just a topological characterization and alternating. Then you can find, and they also give a very nice algorithm to check whether a given knot is alternating or not using the normal surface. And also Josh Green has some more applications, such as I think Josh Green somehow reproved the weak version of the decay conjecture, which says every reduced alternating diagram of an alternating knot has the same number of crossings.
Okay. Oh, thank you very much.
Yeah. Yeah, so he reproved it. And another interesting thing is every positive, I mean, I think he says special, but special alternating, I mean, special alternating means it is either positive alternating or negative alternating, but a special alternating not the separate genus, the minima separate, every minima separate surface is just a canonical separate surface. Canonical means it comes from the separate algorithm. Yeah, I think it's yeah, I think he proved, yes, I think he proved it, and the proof is very short. Originally, it was proven by Jessica Banks, which is like, I think it's at least 20 pages, like using something called the Kakimi's complex. But there, I think the Josh Green's proof is like a 2 or 3.
Oh.
Yeah.
Okay, thank you.
It's basically if it is positive alternating and negative alternating, then like you compare it and you little bit carefully see, then like, it's done. If my memory is correct, then I think there was something like I was very impressed. So I'm pretty sure that I'm right, like 80%, 85% I'm right. Yeah. So
any further questions? Remarks? So if there are no questions, so let's thank again for a very nice talk. Very suggestive, a lot of ideas. So thank you very much.
Thank you very much.
That's all for today.